Sorry.
Okay. Yeah. Okay. Sure. Hello everyone. Good morning. Today I will give a presentation for a paper published in SML 2021, and the title is called Cross Gradient Aggregation for Decentralized Learning from Non-IID Data. At first, I will give some background for the deep learning, and the deep learning algorithm has got a lot of attention nowadays because their ability to learn from large data set. It has been observed that the combination of more data and sufficiently complex model architecture leads to better performance for the neural network, because the ability to exploit the collective computing power of local computing nodes. Distributed machine learning is a promising tool to deal with such diluted data, especially when the data are produced from different locations. Approaches to design such kind of distributed machine learning include two ways. One is centralized approach, the other one is a decentralized approach. In the centralized setting, a central parameter server collects, process, and sends process information back to the agents. A popular approach for achieve centralized learning is called federated learning, which use central parity server and learn from the different data sets that are provided to the agents. However, that kind of centralized approach has some limitations due to the they need to, all the agents need to communicate with the central server, which is in challenge, which have some challenges in several applications for sensor networks, IoT devices, or multi-agent robotics. So, to address this concern, we may consider decentralized learning. Several decentralized learning algorithm has been proposed, where the decentralized machine learning is just like this figure. That means each agent only interact with the neighbors without a central server. There is some previous works on decentralized learning. The reason I show this algorithm here is because they use this paper uses this three algorithm as baselines. It includes the decentralized parallel stochastic gradient descent, and also the stochastic gradient push. There is a swarm SGD also, but all these frameworks have challenges with the non-IID data. We'll introduce one by one. This is the algorithm for the DPSGD here, decentralized parallel SGD. And you can see this result. This is a for loop here. That means this algorithm is a synchronous parallel algorithm. That means all node here usually synchronized by a clock. Each node maintain a local model or xi, xki here, and at each iteration, each node computes a stochastic gradient, and when the synchronization barrier is met, the node will exchange. Each node will exchange local models with its neighbor and average the local model it received with its own local variable, and then each node will update their model using the average and the local stochastic gradient descent as local stochastic gradient. And the next approach is called stochastic gradient pushing. Instead of using the previous approach, they try to change this step here. This step is push sum step. You can see maybe we can push some stuff. It's like send some parameter to alt neighbors and receive some parameter from the in neighbors. And the why here is the all neighbors and the in neighbors, because they consider direct direct graph, just like for zero here, for the agent 0. They can like send its parameter to 1, 2, 4, but I can receive their receive the model from 4, 6, 7 something. This is direct graph. So in this loop here, each node have 3 variables: the model parameter xi here, model parameters, and scalar and the scalar weight. This weight, this is scalar, it's not a vector, equals 1, and because they use push sum like just this is a push sum process here. They just random piece weight from a uniform distribution and normalize them as PIGI equals 1, and if PIG equals 0, PR equals 0, if the node G is not the neighbor of node I, so they generate a weight PIGK here, and send the bears because we times this number right here. The bears gradient model and bears push some weight and receive that from to the neighbors and receive that kind of value from the in neighbors. And after that, so they will this will perform the approximate decentralized distributed average, and the gradient was evaluated use this one, xik plus 1 divided by wik plus 1 here is to the bears the approximate average model xik plus 1, and overall this algorithm is obtained by using one stochastic gradient step and at each node and one iteration for the push sum. So in this algorithm, the paper said they can use generic communication topologies that may be directed, sparse, and time varying, because the things the communication topologies is just like the PGI. They can choose different value for PGI in this algorithm. The next work is called Swarm SGD, and in this algorithm, they try to perform basically or intuitively. They just try to perform some number of local optimization steps or local gradient steps. That's each agent I perform several local steps, and then to average with its neighbors. But the question is, the neighbor here is chosen uniformly at random. That means at each iteration, and they try to random pick a neighbor uniformly to share information and then average the two models here. And the regular graph here, the G is a regular graph, is each vertex had the same number of neighbors. That means the same number of degree. They show this one, these algorithms, and Yeah, just like that. But also there is something for the HIHG. That means the agent I or agent G performs a different number of local SG steps. How these kind of different? They show that in the paper. They mention is they at random times given a clock by a pausing rate to that means HI and HG may be a random number, or when they perform this aggregation. With this algorithm here. Although above decentralized approaches can maybe I mentioned like in the 3 retail workshop. Although these approaches in IID case they can, and the performance of these algorithms can match the centralized approaches, but in non-IID case there still exists a gap in centralized learning, and several approaches fell under significant non-IID distribution. So this paper, they try to deal with the non-IID case for decentralized learning. And this is a formulation here. It's just like a yarn problem, and N here is number of N agents, and Fi is the loss function based on the private DI. And here, this is the overall loss function. The decentralized machine learning will try to solve this problem in a decentralized way, and among all the agents, and the agents are assumed to be communication constrained and only exchange the information with their neighbors. That means that they define an weighted undirected graph, and with HCSA and adjacent matrix pi here. Adjacent matrix is just a communication matrix. So this paper introduced a 2K concept called self gradient and cross gradient here. Self gradient and cross gradient. What this mean? This because for example we have 3 agents here, and we have a model, one agent, one have a model one, and this model will like used to generate the gradient for this model can be used for generate the gradient over the agent one's data. We got the G11. This is this equation here, the self gradient, and this model will share to the agent 2 and agent 3, and they also can use this model 1 to get a gradient over or their local data, the D2, D3, and we can get G1, G2, but G1, 2 or G1, 3. So we got this self and cross gradient here. They try to use this kind of information like cross gradient and self gradient to deal with the non-IID case. The intuition is like in IID case, the cross gradient should be like the IID case, like the cross gradient should be statistically like the self gradient. But in the non-IID case, the difference between the cross gradient in different agents becomes so significant, and the consensus may be difficult to achieve. So instead of just like this one. So how do they deal with this case? They try to seek a direction that a descendant direction that is close to the self gradient, and simultaneously is positively correlated with all the cross gradient. This means they try to the method they use is quadratic projection, quadratic programming projection, just like this one here. They try to solve this problem and to get a new gradient, which will which is close to self-gradient and positive correlated with all cross-gradient. So what this equation mean, like in this special case I show here, in this case, we consider we try to generate a gradient, a new gradient for agent one using the cross gradient or self gradient given one, right? And we try to solve this problem here, just like here, the loss here, you can see that we try to find a z that is close to the self gradient, but we have a constraint that like this all this z is positive correlated with all the cross gradient, and eta one here I used to represent the neighbors of agent one. So
Jiahao,
in this
sorry.
case, okay.
Can I check the cross gradient definition again? Sorry, I missed that information. I was checking a message just now. Yeah.
Yeah, it's just like if you see to the difference, it's just change the data set here. And
J set L instead of J itself.
Yeah, because like each agent will send their model to the neighbors, right? For example, to agent two, and agent two has the model one. They can compute a gradient and send this gradient to agent one. So more specifically, like you can just treat this algorithm. They not only share the model, they also share the gradient.
They share the gradient among the participants. Okay.
Yes.
Mutual gradient. Okay. Thanks.
I mean, I will show this algorithm one step by one step after that. I mean, I will.
Yeah, I'm just curious. Okay.
Okay, so using this kind of QP projection, they can find a good descent direction here. Right? And how to solve this quadratic programming here? This is the primal form. They try to find a dual formulation about this QP, and we got this formula, and which is more efficient from the computational point of view. And once we solve this dual formulation, we can get a optimal dual variable U star, and we can recover the optimal projection direction using this equation here. And this is algorithm of.
Hey, Jiahao, I have a question. Okay. So can you go? Here. So for the method here, they want to find a descent direction that is close to self-gradient, but simultaneously it's positive correlated with all cross gradients. So what's the intuition here? So why this direction is the best? I mean, this perhaps this is the key idea of their cross gradient aggregation here.
Yes. The case is they want to like because the difference between the cross gradient is significant when the data is non-IID, right? Yeah. And they try to find a way to mitigate this kind of difference.
Yeah, if they want to mitigate this difference, well, you gave me 3 directions. Okay, each direction is evaluated on a different data distribution. Then, if I want to, find the best direction, why don't I just, average them and then take the average direction there? I mean, they should have a goal. They should have a rigorous goal so that when they say, oh, this is the goal that I want to achieve, then I, kind of optimize something. I found out that the optimal direction will be calculated by the by the quadratic programming formulation that you mentioned later. I saw that I thought they should have some kind of, maybe should have some theoretical reasoning rather than
actually
heuristic.
no. Yeah. Actually, no, because this approach, the quadratic programming and projection approach is not from here. It's from they have, there is a previous paper focused on continual learning, it's called continual learning. Because in the continual learning, we have new data coming, and maybe when train the model or new data, and the model will forgetting some old data. We forget some old data. It's a process, right? And this is the continual learning. If I understand correctly, and they try to so to solve the forgetting problem. That kind of paper, they try to find a good gradient descent direction. In this way, the model can remember the old information or all data information, and also the new gradient information.
Oh, so
they just borrow that kind of things here.
So you mean that this quadratic programming projection, they just borrow it from the continual learning, right? So they have the continual learning actually come up with this projection formulation, and they borrow it to this decentralized learning, and then they will say, "Oh, I'm going to do this," right?
Yes, the same.
Oh,
they don't influence more.
Oh, okay. Oh, so this this is good. This is the easy way, kind of A plus B. You got a C. Okay, I see.
I want to follow up with Dr. Guo's concern. So if you do this way, compare with the way Dr. Guo mentioned, for example, I take the average. Besides for learning forgetting things, is there any kind of extra benefit, like we can achieve convergence better, faster, or any other extra benefits?
Actually, I don't know. For example, for this algorithm, right? This algorithm, they try to share two stuffs, like the model and the gradient. I don't see like some. I forget. Maybe there's some paper share these two variables at the same time. I forget. Maybe I missed some. I ignored some papers, but I don't know how the average the gradient or average the model will give them more benefit than only share the model only, or only share the gradient, right? So I don't know there's a comparison for that. But this paper shares these two values, these two variables, and using quadratic programming, quadratic projection to deal with to get a good direction. They don't, but also they don't give an experiment just like what you said, linear average for the information. They do not show that.
Because they propose a way, right? So, but actually, if you want to mitigate say that, like you mentioned, you want to mitigate the differences of those gradients, cross gradients. There are multiple ways we can use, right? But they need to tell us why their way, besides the learning forgetting things, why their way is better. Right. For example, what Dr. Guo mentioned is just a very simple way. You put the cross gradient together and take an average of that and send it out. Right. But there are multiple ways. You put some weight over there as well. Yeah.
Do they
multiple way to do the combination?
They don't mention Doppler. I try to figure out that. I read all their papers and all the related works. They don't mention.
Yeah, I get it. But Jiahao, do they have a proof saying that, well, for example, for this cross gradient aggregation, this method, what's their convergence results?
Yes, I will show that.
Okay.
I will show. But I want to show that they don't. The convergence rate is the same.
Convergence rate is the same as the centralized one, you mean?
Decentralized, I believe. Or
Decentralized. It's all the previous reach work I just mentioned, the same name, same amount, like 1 divided by square NK.
Oh, okay.
It's the same.
For non-ID case or for IID case?
Not of course. Non-ID they define, but they not for non-convex. They only consider for non-convex.
Yeah, I was thinking that to answer Dr. Pan's question, for example, if you just use the average, and then first also use this complicated quadratic programming, and then you may can derive 2 different convergence results. Then you compare, you analytically compare those 2 methods. Perhaps you will be able to see maybe under some situation, the quadratic programming approach is better. I mean, they analytically, I feel that maybe that's it's possible for them to compare. Or you can do this, Jiahao, you can do this. So for example, for their quadratic programming, right? The method, you just gave them a very specific special case for this quadratic programming approach, so that their solution, the optimal solution is the average case. And then you can reuse their convergence results, right? You can still reuse, just give them a very specific value, then you will be able to see maybe there's some kind of differences.
Yeah, I see. Yeah, I understand. Just like the in papers, they show they have a simple function to show a toy example to show is the objective is inconsistent among the agents.
Yeah,
you know that.
I get maybe that's the easy way, to show that.
Yeah. Okay. Actually, their algorithm, this is in algorithm 1. It's just like the moment variant of consensus SGD. It's just one paper or one a paper one of the author proposed. I mean, it's just a moment variant consensus SGD, but with quadratic projection here. And yeah, just like this one.
Jiahao, I have one more question. For this one, is it based on the directional graph, or is mutual directional graph?
Oh, good question. Let me think. The dimensions is
I mean, if it's a graph without direction, it's like okay.
Here. I mentioned. I mentioned like that here. I think I have something to say here. It shows like an undirected graph.
Undirected. Okay.
Undirected.
Okay.
Okay, let me go through the algorithm here. And this algorithm is just like that. Each random, each agent J will calculate its self-gradient J in each iteration. And then like each agent J will send their parameters to all other agent L in its neighbors, the neighbors at C, and get the cross gradient and transmit back to the agent G and stack up into a matrix, big matrix, capital G. And after we got this one, this is the figure. We got these 3, right? This is a big G in big G here, and then followed by WKG. Here is a consensus update. That means the consensus to get to average them neighbors model and G, and then followed by a project progression approach. And this part is a momentum acceleration momentum, and then we can update the local model. Yeah, finally each agent will do this way and get the new model iteration. You know, the case is they require multiple exchanges of the multiple parameters and the gradient between the neighbor agents in each iteration. So they try to find a way to make their algorithm communication efficient. So what they do, they try to integrate the CGA with error feedback to reduce the communication overhead. The error feedback is like this. First is like GT is a gradient, and then followed by error correction, and delta T is compression, and ST, and update the model and update the residual error. And this is their compressed CGA. And compare with the compressed and the original CGA, it introduce several steps. The first one is introduce a scaled sun gradient. So here, scaled sun gradient, and also here is the error between the compressed gradient and the non-compressed gradient, EIG, and use this error to do the error correction. And also this for loop is also used for calculate the cross gradient and do the compression and error correction. So this is the compressed CGA. I will show the convergence analysis. It includes the three assumptions. The first assumption is this is the overall objective problem, and assumption one implies that the fx is L smooth, and assumption two is assume that the boundedness of boundedness due to the net is the first, that's equation 7 here. This is to bound the variance with the same agent. You can see I here. And this equation, or this inequality is to try to bound the variance among different agents. Compare with other other approaches, this paper have a unique assumption like this one. This is necessary because they introduce the QP projection. And projection, that means that if the local optimization problem is meaningful, the assumption will hold. And the value of epsilon here and is governed by the difference between the data distribution processed by each agent. Yeah, they have a unique assumption. And here is a consensus rate. They show that they only focus on non-convex objective function. And this theorem shows that the CGA achieves a consensus among the different agents. And like you can see this like a consensus rate includes two forms. One is this first part and second part. And in the first part, there is three terms, and the row here is the spectral gap of the communication matrix. And the epsilon here is the controlled by the assumption 3 by this one. Which shows that how well the local projective progression is solved, and And this part is related to sampling variance. And this part is indicates the gradient variance, and which is determined by the data distribution. And also, like you can see, this term can be like adjusted, can be tuned to be reduced by using the step size alpha, and the beta is a momentum coefficients. And this term is a summation of a square norm of average gradients. And this term also can be controlled by reduce by tuning the step size and moment efficient beta. Next is a convergence analysis. The first is they show their algorithm achieves the convergence with this formula. Like we can see when k increase becomes sufficient large, this term will dominate this overall error, right? And which is achieves collinear speed up across. I mean, by the way, all other algorithms, they can I mentioned before, they can also achieve the linear speed up. And this convergence result matches the well-known best result in decentralized SGD algorithm. And I want to say, like, because these papers, they consider two algorithms, right? One is the CGA, the other one is they use a compression called the compressed CGA. They don't prove the algorithm, the convergence for compressed CGA. They just said, like, we can hypothesize that, we can think of, we can guess the compressed CGA still satisfy like this one, the linear speed up. They don't prove that. Next is the evaluation for this paper. They consider the baseline algorithm, these three, and they consider CFAR 10 and MNIST. They consider number of agents 5, 10, 40, and they consider like several communication graphs fully connected, green and bipartite, which is from dense graph to sparse connection. And they consider a neural network model with a specific structure here. But they also try to the VGG and or on the CFAR 10, but I don't show here. They show in the appendix. And also I don't introduce a means result here, but because they show the result in the appendix, I only introduced their result on CNN model with the CFAR 10 here. The first convergence result is for the training for the CG. That's like the whole different model structure, mean the communication graph affect the convergence under the IID and non-IID distribution. And we can see like there's three curves. Right? The red one is fully connected, and blue is ring, and this green is bipartite. And we can see that like oh, by the way, this is training, and like the faster rate for can achieved by sparser topologies, right? I mean, we go down like the graph become more sparser, and the loss will decrease more. And even happens for the in non-IID distribution, it's still the same like same things, but it's have more this stuff, right? This like variance here is because the like training process have in non-IID distribution to have more gradient variance and variation. But you
so why? So this result is weird. You know, here, for example, for the left figure, the fully collected, you have the most collected topology. Then usually you should have a high, faster convergence speed because you are more collected.
I think you need more epochs to to be more accurate. I mean, less, not loss. I mean, if you go to infinite, probably fully connected is better than the other two. But if you give a limited number of epochs, probably those sparse graph will be better than the fully connected. Because the fully connected, I guess it needs time to, you know, to get the best result. I'm not sure if I understand it correct or not. Yeah.
Here, I mean,
if you check, I mean, you can check other decentralized algorithm, their experimental results.
I have checked. I have checked them.
Do they match with each other here? For example,
yeah, this is a good question. Let me first finish. Okay, this part, right? Even like there is a delta, right? But when we more epochs is achieve the same value, right? Okay, that introduce like why this will like there's this phenomenon here. Because like they mentioned the federated learning paper, the original federal learning paper, like in 2016, right? They do a lot of experiment of federal average and stuff. In that paper, they found like that kind of paper observed the similar phenomena like this one, sparser well better than the fully connected. For it since like they consider like in federal learning we can consider the participation of the agents, right? And again the partial participations. They show that like they said that like in that paper they show the similar phenomena like this one, and also they show that in decentralized learning, one of the author's paper they have the similar result. Let me show you here. This is the two papers they mentioned to achieve the similar. That means you can see here. This is a fully connected. This right here, and the sparse topology is here, more sparse. The training. This is one of the author's paper's result.
Oh, okay. So, so this right figure is for IID or non-IID?
I forget, but
okay.
I forget. But the case is no matter non-IID and IID, they both the same thing, right? I just mentioned. I mean, I just show in the previous I just mentioned. They show the non-IID and IID both like full connected is worse than the sparse.
Oh, really?
Topology.
I didn't know. I never realized.
So, what is the intuition behind that? Is it because like the fully collected does not exploit like the relationship among them? So the useful information may be hidden in the final results?
This is a good question actually. I tried to figure out by myself. There like say in the paper they only mentioned one sentence that like this is maybe this is phenomena may be attributed by the dense communication in the fully connected layer, phonetic network. So there's no explanation, and I try to figure out from the theoretical and also this paper they don't mention why this happens. But you can see this is like very tricky, something like look at the random RAM. The result, I mean, also like I try to figure out like in they mentioned the federal paper. They have the similar phenomenon. But when I check the paper, only this figure shows some things happen like show something like for this dot line here, the federal average C equals to 1 means C equals to 1 means like all the client participation, and C equals 0 means only one client per round. So this you can see this from here to here, the participation will decrease, right?
Mm-hmm.
And that means the communication is sparser. So the testing accuracy higher. Whereas you can see the formula number. I don't know why. I don't know. There is a tricky thing like this is for training, but this is for testing. So here we only show like in the training we have this formula, we have this phenomenon, but in the testing they don't have this phenomenon in their paper. Let me show you. This is the training and testing for accuracy. You can see like the IID case like this one, this training is still the same thing, but for testing, this is the testing. And you can do almost the same. And for this part, this is also the testing IID. You can see the fully connected layer achieves better than others. So I'm also confused, like why the testing accuracy does not have that kind of phenomena like the training accuracy.
Yeah. The testing accuracy, you cannot rely on the testing accuracy to tell you those kind of things, because the testing accuracy is very related to the tuning, and also the training accuracy is more reliable compared to testing accuracy. Testing accuracy, you have too many things. There are other things that you need to consider besides the optimization performance.
Mm-hmm.
That's the difference between learning and machine learning and optimization. They are different areas actually. Although many people think they are the same, but they're actually different. But you can rely on the training loss or training accuracy to tell you that the true loss here. Well, there are some kind of patterns you can observe. Testing accuracy, there are a lot of randomness there, and sometimes even if you have very high training accuracy, your testing accuracy may be bad. That's normal.
So is this paper accepted?
Yeah, accepted.
Because when I search online, it seems like it's an archive paper. So well,
yeah, it's archive, but like this year's SML.
Okay.
Yeah,
it's interesting. Proceedings of SML.
Yeah,
Okay.
It's interesting. I didn't. I never thought that sparse topology is better before. Yeah.
At the end of the day, if you give enough training, they achieve the same results, right? They only probably, I don't know.
For the training, they can.
Yeah. Could you go to the 19 or something, page 19? Yeah, this page. If you have enough training, they all achieve the same results.
Yeah.
So you can only see probably, I don't know, it convert faster for the sparse graph.
Because like the sparsity of the graph dominant, affect the row here, the communication row here, special gain. And this row will affect the consensus rate and something related.
That's true. Intuitively, fully connected graph, you have more more connection.
Interaction.
Yeah, more interactions. So probably given limited epochs, sparse graph will converge faster. But at the end of the day, they have the same training loss if you give enough trainings.
Yeah, but I don't know. Yeah, this is the case. I try to figure out, but no, still no things happen. I don't know. I still figure out like why this figure is for the original federal paper, right? They show this one. They consider federal average, like with the full participation, and others with only and this is only one client participation each round, and also in the middle 10%. But when I see other papers, they do not show. But this is also for test accuracy. Test accuracy. No, it's something
random.
like
probably.
Yeah.
We need to.
Yeah, on the non-consistent with the other papers also. I see other federal learning paper. They try to focus on the number of agents increase, and number of participation increase and decrease. They do not. Maybe they don't find like this one, right? Have you guys like read some papers focus on the participation rate and how this participation rate will affect the correlance?
But the thing is, if for non-ID case, do you think the number of participations, numbers of participants, has any kind of a correlation with, the convergence rate or something, or the training loss or something? The speed of the training loss, I would say. The more participants, we have, convert faster.
Yes, Dr. Like this one here, this is our loss. There is n. N is the number of total number of agents. In the participation for learning, there should be a S or something that is a partial of n. You increase n, you will reduce more for the loss.
What is the K here?
K is the total number of iteration, the number of iterations.
Oh, okay.
Iterations.
Not sure, but still that's a bound, right? So
yeah, I know. Yeah, this is a bound.
Yeah.
Yes, right.
The number they choose is 5, 10, and 40. So probably you may not be able to show the advantage of that.
Okay. Yeah, let's show the. Okay. Here, this is the testing accuracy stuff. They show like a 3 graph and a different number of agents, 5, 10, 40. And you can see that like you see the bold one is the best. This is the 2. You can see that like the CGA they propose is comparable or slightly better than other methods in most cases, right? And however, like the testing accuracy for SGP and SWAP SGD with 40 agents, and also in the running and in run and bipartite here, it reduced a lot the testing accuracy. And
okay, it's a DPM SGD. It's very close to that one. I mean, CGA is very close to that one. If you see CGA's number, almost probably only 1% increase or something.
Yeah, yes, you are right, Doctor. Because the only change of DPM SGD and no, because DPM SGD also use momentum. Momentum may be better. Momentum information.
But what I care about is for the DPM SGD, do they do something like the CGA, increase a lot of local computing overhead, burden, also
no,
very
no.
communication intensive?
No.
So yeah, I'm not sure, because this kind of paper, you achieve 1% better at a very, very high cost, right?
Yeah, I know, but I show this is only for non-IID case. All these better convergence.
Okay.
But this paper try to deal with the non-IID case, right?
Okay.
And here, there is a non-IID case. You can see the DPM SGD diverge and in the 5 agents, 10 agents, and some 10 agents, and also it's very low accuracy, right? But their algorithm achieves the best.
Okay.
And also like their compressed version also like but it's slightly lower than CGA, but higher, for example, these two higher than other algorithms, right? So, which shows using quadratic progression because it's better for non-IID data distribution.
Still, I have doubts about this kind of, decentralized learning across non-IID cases. Is there any kind of potential applications for that? I know that's a very good theoretical study material, but in practice, can you say in the near future, or probably in the future in general, the things is going to fly or not?
I don't think so, no, because like non-IID cases appears like almost every data set in real life. Like
no, I mean the decentralized learning. I mean across the non-IID case. I'm not talking about, say, like the fair learning, you have a server structure. Yeah, what I mean is a purely decentralized, like the things you mentioned here. Another example is in wireless communication, right? We always talk about ad hoc network. That's a very good theoretical study material. People study that for many, many years. There's tons of paper about that. But these things never fly.
Yeah, I know.
Yeah, nobody use that because it's too complex. This is the same thing, it's too much communication and computing burdens for the nodes. So I think probably if the server is connected by the internet, somehow they can accept this. But for the general further learning application scenario, well, that's too much. It's just too much.
Yeah, I know. I understand. Like they find a very complex way and unpractical way to solve a problem. Like
Yeah, theoretically,
a very extreme case.
Yeah, it has a very good value, but yeah, I'm just worried about
that is a true. That is so most of the paper do research like this way.
Yeah, I agree. Like I mentioned, it's like ad hoc network. If you search for that, there are tons of papers. You can never ever finish reading of that. But the things never be used. But I don't know in the far future, but in the near future, I cannot say. Even today is almost the end of the era of wireless communication or networking. Still, nobody is using that, right? So. I'm worried about, machine learning probably had the same trend. We study very, very complex problem, machine learning over the graph and stuff like that. But at the end of the day, nobody's going to use that because it's too complex.
Yeah,
too many uncertainty things there.
Yeah. Yes.
So, anyway, that's my that's not that related to this paper. It's just my personal concern. Yeah.
Okay, here like you show the comparison with other two SGP and swarm SGD's average training loss. The reason is why we show these two figures is because like CGA introduce more communications, things like they transmit the model and the gradient, right? Or communications. How this will affect the convergence. And when we consider that kind of communication in this plot, they show that this plot show the average loss with respect to the communication runs here. They show the algorithm still converges lower values after 200 communication runs, then add to baseline. Finally, is a conclusion. So this paper, they propose a CG algorithm to effectively learn from non-IID data distribution in a decentralized manner. And they present a convergence analysis for proposed algorithms and show they can match the well-known convergence rate. And they also propose a compressed variant of their algorithms and show its efficiency.
Okay, can you see my screen?
Yeah.
Okay. So today I will share this paper. So certifying the freedom buyers. And this paper was published for the NIPS 2020, and all these answers are from Angular. So before I introduce the certifying the confidence via the randomized smoothing, I need first adversary example and corresponding and method randomized smoothing. So previous research found that most machine learning models that are lack of the robustness. So for example, that as an example, and using this pandas image and model can that the panda is higher for this image, but we add some handcrafted and this well designed noise right side, and then this time it has this using this model, and this model will it will run. So such phenomenon shows the machine learning models obviously is the unrobust. So this may bring the threaten to implement models. But for example, there is a noise to the outside.
Zhidong, I think you may need to adjust your microphone because we cannot hear you clearly.
Okay. So, how about now?
It's fine now.
Okay. So. So consider this upside. So if we add some adversary knowledge upside, and the machine learning models will give totally wrong prediction result. And to defend this against such adversary attacks, there's randomized. So basically, randomized smoothing is a majority voting technique. So so how we do the randomized smoothing? Firstly, we so consider we have a base classifier, and which housing, and then the smooth classifier is defined as this. So because we add the noise input images, so the output of this variety. So we use the most appropriate by this base classifier of this random Gaussian corruption of the X. So for example, take this pandas image as if we query this X with this random noise, and we query many times, and so finally we can probability. So and this time we will use a class as the final prediction. So this time panda is larger probability, and we will leave this image as panda. So this smooth classifier, in fact, it is the it is a transformation for the base classifier F, and if we shift this this Gaussian noise, and the probability of each class cannot change too much, and so we can use this property to certify the smooth classifier's prediction. It will not change, and if the input change not too much. So mathematically, so if we denote PA as the probability of and let P runner-up classes, and the radius of this of this our test example can be calculated using this formula. Here, this phi is the inverse standard Gaussian CDF. So this is a traditional randomized smoothing, and we make the prediction. So as the top class, and we return the radius R using this method. How auto or shortcoming is. So the first thing is that has too much information about class label. So the smooth classifier has the limited capabilities that make the output difficult to use for this decision making. Because for consider the base classifier, but it have a softmax layer, and the output is score, and such confidence score can be interpreted as degree of certainty that this model has to each class labels, but for the smooth classifier have this. So the second thing is because in randomized smoothing, each random property image we vote either or guess the most likely class, and we ignore all the other informations about how confident this network is for this class label. So this may need a scenario where the image may has a large certified radius, but the underlying classifier may have the confidence. So for example, here the radius and is for example here is large, but the score is small. For example, take this point as an example. So this is counterintuitive. And to address these problems, so the answer proposed the certifying the confidence. So certifying confidence, it is based on randomized.
Sorry. Could you let me check the definition of the certified radius again? How do you define the certified radius?
Okay, certified radius it is
That's P.
Okay, so if so here we have a clean example X, and around this X we have a radius R, and within this radius R, for any example, within this circle, within this radius, the model will return the smooth model will return the same prediction result as this X.
Okay.
this is why they call the certified.
So yeah, PA is empirical probability, or is kind of probability.
PA is not the empirical probability. It is the PA is the probability that estimated using the Monte Carlo method. So for example, we take the 100 times query and 90 times query. So it will report 90 times query. So it votes the standard, and this time it may be equals 90%, something like this. Not the average of this.
So in other words, the radius is also kind of a very rough estimation, right? So if you want a better robustness, instead of use the the metric like the radius, you use more complex metrics like the confidence level or something, right? Just like for stochastic optimization, the simplest way we're using the mean value. But if we wanted more statistical information, we use the divergence, we use some other definition similar to that, right?
Yeah, similar to that. But here in this paper, because in this randomized smoothing, because we only return the top classes as the final prediction. So this smooth model will only return one label. So it will return which label is corresponding to this image. For the for other labels, it will not report. And so this is one shortcoming. Another thing is randomized smoothing. The radius is not correlated well with the confidence score. That means the confidence score is large.
I think it's a one-dimension information. Definitely, if you use something else like divergence or something, it has more richer. It has a richer information compared to the one-dimensional stuff. Okay.
Yeah.
Thank you. Yeah, go ahead, please.
Okay, so for the certifying confidence, so here the smooth classifiers now it is applied as the expectation over the base classifier, and this is different from the previous randomized. The previous randomized applied as argmax of this one, argmax of this base classifier. And so here, the goal also changed. Previously, randomized smoothing aims to certify the prediction result will not change. But here, we want to certify expected score. The expected confidence score will not change much. So, more precisely, so here we want to certify the expected confidence score of this class over predicted class I. It will remain above a given threshold, and this threshold definitely should be within the interval from A to. And here AD it is the model's output range. And the main result of this paper is, so if we let this EI be the lower bound of the expected score SI, SI, and if we define TI as this EI minus A and minus A, so the conclusion is, so for any population X line of this in input X, and we have current within this radius R, and we have the Fi X prime, it is definitely, it must greater than this one. So this time we can make the certified score, certifying the confidence greater than specific values. And this specific value is depends on the lower bound, that is the loss function by and then so in the experiment, so the same as the randomized, this lower bound probability EI is estimated using color method, and the lower bound, so it is estimated using the Hofstadter quality. So it is using this formula, and in this formula, number of experiment times. So we query this classifier m times, and after we obtain the score and we average it and adjust it with this term. This term, so here this alpha success rate according Hofstadter's inequality. So it's just a threshold error successful rate of quality, and we calculate the any problem? Okay, so if not, I will go to the experiment part. So in the experiment part, the experiment or they report the certified accuracy, and
so do you mean that, for example, using their confidence versus using those regions, they can achieve higher accuracy, or is that what you mean?
Yes, they achieve the better result. In fact, this without CDF result similar with the original randomized.
Okay.
This is dash lines.
Okay. So basically they have tighter analysis, tighter proof process, so that they can derive a higher bound.
Yes, in fact, they modify the lemma Paris lithium, and this is the basic lithium used by smoothing. They modify it to adequate this version.
So is this I mean, for example, for any other paper in the future work, for example, if other papers, related paper, they are using the certified radians, they still use the original certified radians to do the analysis, but now you are using this confidence to do the analysis. So you are for sure to outperform others. Is that right?
Yes.
I mean, no matter, what kind of new method you are using, as long as you are still relying on the radians to analyze them, I can use the confidence to analyze that.
Yes, you are right.
Well, yeah, that's fine, but the problem is that, well, that means that perhaps you don't have any contribution if that's the case, because the others, they have provided a new analysis method, and now you are trying to apply this analysis method to some existing tactic. I mean, then people will ask you, so what is your contribution? Right? It's very hard for you to do anything unless you say, okay, their analysis method is not good enough, I'm going to improve that. Well, unless you can do that step, otherwise this paper, the result is fine. There's no doubt about that one. But I mean, it's more like a dead end, unless you can improve the analysis method. That's the only thing that you can do. Otherwise, you still want to focus on maybe better robustness method rather than a better robustness analysis method. You get my point?
Yes, you are right. It's hard to reuse their matter the same or out.
Yeah, that's what I'm saying. Well, this is maybe this is just for example, for the evaluation part, experiment part. You can use this method so that they will give you a better curve, look like this one. But if you are, but in terms of technical contribution, you still want to focus on the method. I mean, the robustness method rather than this analysis method.
Yes, I got.
Okay. Yeah.
Okay.
Okay. Go ahead.
Okay. That's all. Present.
I'm not sure if I understand correctly. It seems they provide another metric, or say, they provide another way to interpret the existing metric, something like that.
I think what they, I think they are. So it's basically like they say, oh, I have a method to improve the to provide the robustness, and then this method they will give me this curve, for example, this dashed line curve, and now they say, oh, when you derive this dashed line curve, looks like your analysis is not tight. So let's do a better analysis so that I can give you a tighter bound. I think that's what they're doing.
Almost there, but I think the most the biggest difference is there. The smooth classifier is different. Previously, we defined this smooth classifier as the argmax f x plus delta. Now it is defined as the addition of this one.
Before is still this one, right? You check the expectation, and then you take the maximum. I still the same. This classifier is still the same as the original classifier, right? The smooth classifier.
No, I don't think so. Previously,
you can compare.
Previously, with argmax, which we previously it is I think it is.
Yeah.
The argmax should be within the expectation.
No, you cannot do that. So how can you argmax a random variable? You cannot argmax a random variable. This one, remember, this one is a random variable. Here, this is a random variable. I mean, this one, this is a random variable. You have a test data set, you have a random variable there. Then this one will return you a random variable as well. How can you argmax a random variable? I don't think so. You check it out. It looks like they are still using the same this one. So this is a probability, right?
Yes.
So now
this different.
Probability you think about is like expectation.
I think they are not equal. Consider the experiment part. So what we do here in the experiment is we query each x, we got the prediction score, and then we use the argmax, got the predicted label, and then we have several labels. We use this estimation method to got the probability lower bound, and then using the lower bound to calculate this radius.
Well, you consider you have an x. This is a test example, and then you add a random according to your formulation. You add a random variable. Then this is a randomly perturbed example. Then you have you go to f the classifier. They will return you the label factor the score factor. So they will give you different score factors based on different realization of this delta. And then what you do is that you just add them together, take the average, you get a unique prediction score, a single average prediction score. Then you take the maximum from this score, the index with the highest score here. And then this is the prediction process, right?
This is this paper's process. But in the original randomized, it is after we got the prediction, we got the prediction score for each test. We will do we will aggregate first, and then got a prediction label, and then we use this label to do a majority voting and got the final prediction label.
You mean, so you mean for this one, they are doing, for example, because different realization of optional, they get a score factor, they get a lot of score factor. So for this one, you know, well, which label, for example, they are prediction C1, they are prediction C2, this one prediction C3, Cn or C1, then they do a majority voting here on the result.
Yes. Yes.
Oh, okay.
So finally, they obtain a better result.
Oh, so you mean that they actually do change a little bit about the prediction method.
Yes.
So, and then because of this change the prediction method, so I can achieve a better accuracy.
Right. Yes. Because in the original randomized smoothing, we use the hard constraint because we must use the largest predicted label. Not majority. So we also store information on this from the label from the score vectors. Now we use the average. Can average this information, and in the experiment part, this number is threshold they predefined in the experiment part. So this number, so it is a threshold that this score function greater than its value. So previously we are certifying this prediction score must greater than physical value. True, therefore it can greater than not a fixed number. We can change it. So this accuracy much better.
Yeah. Okay. But if that's the case, you can, for example, pick up some other papers if they are following the radiance, the certified radiance approach, then you modify it with the certified the confidence one. You may be able to get a new results. Yeah, I'm not sure, but it looks like the contribution is still not enough if you just follow that way, unless your problem is very new.
Yes.
Well, you can try. You can try. You can try it if you want. You know, pick up some kind of new problem, and then you know if they are just starting to consider this one using the old method, you replace it with the new method. But you are because they are it's the topic is still relatively new. Then you may still able to sell it. Otherwise, most of technical contribution looks like has been it's in this paper. So that's what others will question you if you submit such a paper. Yeah, anyway, yeah, just my random thinking about this one.
Any other questions?